Good. So I think we can start. I will be introducing the speaker today. Thanks everyone for joining to this new seminar of the Cambridge Ellis unit. First, I would like to thank the sponsors of the unit, Invenia Labs, Microsoft Research, ARM, AstraZeneca, Cambridge Innovation Capital, IQ Capital, Second Mind, and Schlumberger. Today we have Hana Chockler with us. Hana, she's a principal scientist at the startup company Causal Lens. The mission of this company is to apply causal reasoning to a wide range of domains. Hana is also a reader in formal methods in the Department of Informatics at King's College London. And before joining King's College London, she worked at IBM Research in the formal verification and software engineering departments. Hana's research interests include formal verification and synthesis of hardware and software, and most recently, causal reasoning applied to AI. And today she's going to talk about the actual causality, explanations, and fairness. I'm going to stop sharing. I think, Hana, you can
I can start.
Your slides.
Sure. Thank you, Miguel. Okay, I'm going to share my slides. Yep. Looks like it's working. Okay, so I will start. Please interrupt me and ask questions in the middle of the talk. I also opened the chat window on the side, so hopefully I'll be able to glance there as well if you'd rather type in chat. Okay, so yes, so as Miguel said, I'm going to talk about actual causality, explanations, and fairness. And the plan is that I will first introduce a little bit of theory of actual causality in a very informal way. And apologies to those who already know the theory. And then I will show how it is applied to reasoning about explanations, and most recently about fairness of systems. And the unifying theme here between explanations and fairness is that in both cases, we're talking about black box systems, so neural networks or something that we really don't want to look inside. And yet we're able to reason about them even when most of the system is black box, just purely by interacting with it. So as Miguel said, I have dual affiliation. I'm a principal scientist at Causal Lens, and I'm also faculty in the Department of Informatics at King's. So first I have just 2 slides about the company, just to explain why. But I joined the company last February. I've been at King's for almost 9 years now. So those are 2 slides about Causal Lens. Its mission statement is that causal AI is the only technology that can support human decision making. And the idea is that we construct causal models that can provide users with insightful and accurate information based on causal reasoning rather than correlational. And we take into account the domain expertise that is provided by human experts. We plan and design optimal interventions for achieving the desired outcome. We evaluate hypothetical scenarios, providing predictions, which are very important for making decisions. And all this is done by taking into account constraints. So for example, some of our customers, like all of our customers, are businesses, so they naturally have business constraints. Of course, there are also legal and environmental constraints as well. And the platform looks like this. So we have the data cleaning and discovery part, which collects data, including proprietary data that is supplied by the customer, and the data that is publicly available and gathered from external sources, and automatically discovers valuable data, because usually data that is acquired is not good enough by itself, right, to start reasoning about. So we do some dimensionality reduction, feature selection, and also some analysis of similar types of data, which we can clean it up a bit. Then we automatically build and operationalize causal models. Operationals, we prepare them to be used for decisions. And then once the models are built, so by the way, they're live and they're adaptable and they are updated all the time based on new data. Once we have them, then we can use them to support human decision making. So we can answer the questions in business context, such as designing optimal interventions, predictions, simulating the effect of interventions to show the users. And those are wrapped into apps per industry, tailored to each industry in which we have customers. And they are accompanied by explainability applications that highlight the relevant parts of the models that we used to make this prediction or to suggest this intervention. So that's about Causalence, which is about building causal models. And now I'm going to talk about my work, which actually is no way related to the product. And the reason, of course, for us by keeping this completely separate are the IP issues. So now none of what I'm explaining today is in any way incorporated or is supposed to be incorporated in Causalence product. Right, so now my work. So I'm going to describe work in quite a lot of papers and also mention some papers of other people. When it's my co-author's work, I'm not going to cite it explicitly, but I do have a bibliography slide at the end. When it's somebody else's work, hopefully, I will not forget to cite it on the slide itself. And I'm sure there is a lot of work that I'm not mentioning, so apologies in advance. Right, so some very hand-wavy background on actual causality. So the question of causality, like when do we say that A is the cause of B, right? This is causality, is going back to Hume, 1939. The paper is dated 1939, and the book 1940, the Treatise of Human Nature, where he posed the question. So Hume was a British philosopher, so David Hume, right? So this is like one of the few areas of computer science when we can cite papers from 1739, which is quite nice. So Hume suggested counterfactual causality. A is the cause of B. If had A not happened, then B would not have happened. Right. So, for example, when we still used to have in-person meetings and seminars, since the weather in London is reliably rainy, it would have been a perfect example. So rain is the cause of me being wet, right, arriving drenched to the meeting. And in a little bit less hand-wavy way, which is also, I think I'm going to the territory of Lewis, who was another philosopher in the beginning of the 20th century, it's 1930 something. It's still hand-wavy, right? We're still not in the area of formulas. So the definition would look something like, so we have a world in which A happened, it rained, and I'm wet. If we take the same world exactly, the same London, the same everything, the same day, the same me, but it's not raining, then I wouldn't be wet, right? So I wouldn't have been drenched. Okay, so this counterfactual approach to causality is definitely, it conforms to our intuition. However, it doesn't capture complex relationships that and connections that are needed to make it useful for practical applications and in general actually to reason about philosophical problems as well. So I'm not going to name all the problems because I'm trying to avoid putting formulas and formal definitions on slides. I'm going to mention two problems that arise with a simple counterfactual definition. So first of all, so we have the redundancy, which is not captured by simple counterfactual, so illustrated here. So what happened if it is raining and also I was walking on the sidewalk and the car drove by and splashed on me from a puddle? Now, is it rain or car a cause of me being drenched? So clearly, if we apply just simple counterfactual reasoning, none of those is a counterfactual cause, because had it not been raining, I would still be drenched because the car splashed on me. And had the car not driven by and splashed on me from a puddle, I would still be wet because it was raining. So clearly something is missing here. Something else is needed to capture this causal connections in presence of redundancy. Another example of something that a subtlety that is not captured by the simple counterfactual definition is a preemption. So, so here, for example, I left the house at 8, and the car splashed at me at 8 when I left the house, and then I was wet. And then at 10 it started, so it wasn't raining, but then at 10 it started raining. I was still en route, but I was already wet. Right? So in this case, we would like to say that car is the cause of me being drenched, but not the rain, because I was already drenched when it started raining. But this is not again captured by the simple counterfactual reasoning because of the exactly same reasons. So had the car not been driven by me at 8, I would still be wet by 10 because it started raining, right? It's the same, like symmetric argument would work to show that rain is not the cause either. So something is missing here, some information is missing. So the concept of actual causality defined by Halpern and Pearl in 2001, so also quite a long time ago. And since then, so 2001 was the first paper, then it underwent several transformations. The last definition of causality is due to Halpern 2015, but I think we're going to stop at one before last. Due to technicalities, I prefer that one. I find it more useful. So actual causality, the concept of actual causality extends the counterfactual reasoning by having expressive causal models, allowing redundancy, preemptions, and complex causal structures. So they do allow us to express dependencies between variables as equations, causal equations. They do, and they do allow us to capture redundancy and preemption. So redundancy is captured specifically, for example, by introducing the concept of contingency. So let us now try to define causes that will work even in presence of redundancy. So A would be a cause of B if there exists some contingency C, which is a change in the current world, in which B counterfactually depends on A. In other words, so we have an original world in which A happened and C happened, where C is some other set of variables, and B occurred. And now, so just switching A to not A does not cancel B, does not negate B. But now, okay, so we're doing it in 2 steps. First, we introduce a contingency, a change in the current world, which is changing C to not C, or, in case of multivariate variables, it's going to be changing C to some other set of values. So there is still A still holds and B still occurs, but now in this modified world, B actually does counterfactually depend on A. So now in this modified world, now if we turn off A, if A doesn't happen, then B wouldn't happen either. So it's taking the current situation and bringing it to the edge, so to speak, right, to the counterfactual dependency. And let me show you how it works on the example of the car and the rain. So remember, right, the story was that it was raining and a car splashed on me from a puddle. So I am wet, right, but for 2 reasons. So there is a redundancy, even though one would have been sufficient. So now let's see how it works in actual causality. So contingency in this case. So if we want to say that rain is a cause of me being drenched, then the contingency is the car. So we switch the car off, right? The car in this modified world doesn't drive past me and doesn't splash on me. And now in this modified world, rain is a counterfactual cause of me being drenched, because now indeed if it doesn't rain, then if it had not been raining, then I wouldn't have been wet, right? So this is how actual causality deals with redundancy, and there are ways to deal with preemption as well as capture some complex causal interactions. So, so this was a step towards making causality more useful, right? Because it included more cases of causal dependency that were not captured by simple counterfactual reasoning. But what it lacked was a quantification. So now we could still say that something is a cause of the outcome or it is not. As we know, for practical applications, we usually need to rank things. So because there are too many causes, or we are only interested in most influential causes, or want to compare which cause is more important than the other one. The quantification is important. So here we have responsibility, which is fortunately a quantitative measure of causality. So this work is from 2004, again, quite a long time ago. So what we did is we introduced, this is co-authored with Joe Halpern. We introduced a number that accompanies each cause to capture the extent of causal influence of this cause on the outcome. So let me just explain it by using a simple example. So we have, so this is the story of elections. In 1864, in the United States, of Lincoln versus McClellan. Hopefully it's far enough in the past so that nobody has any feelings about these elections. And we know, so it's historical fact that in particular, Lincoln won in both California and in New York. Now, I don't know what was the percentage, what was the exact result with which he won, but let's assume for the sake of the discussion that each state had exactly 100 voters, and that a draw is not a win, so you have to get at least 51. And the results in California were 51 to 49 to Lincoln, and in New York, they were 90 to 10 to Lincoln as well. Again, I don't know whether this in any way reflects the proportion in 1864. So in both cases, blue voters, each of the blue voters is a cause for Lincoln's win. But what we would like to say is that in California, each of the blue voters was much more critical, right? Much more important for Lincoln's win than in New York. Because in California, as you can probably see from the picture, each voter is critical, right? It's counterfactual, is a counterfactual cause for Lincoln's winning. So if one blue voter changes their mind, then Lincoln is not winning. Whereas in New York, this is not the case. Okay, so we need to distinguish between the cases, and we distinguish them by adding this quantitative measure of causality. And so what happens is that this quantitative measure is defined as using the size of the contingency that we need in order to bring it to the counterfactual case. So if the size, so it's formally defined as 1 divided by 1 plus the size of the contingency. So if the cause is counterfactual already, then of course there is no contingency needed to bring it to the counterfactual case, meaning that the size of the contingency is 0. And therefore, in case of California, each blue voter is 1 responsible for Lincoln win, right? It's 1 over 1 plus 0. Whereas in New York, I think it's easy to see that the size of the contingency that is needed to bring New York to the counterfactual state is 39, right? Because if 39 voters change their mind, blue voters change their mind, then we are again in the same situation as California. So therefore, each blue voter in New York is 1 over 40 responsible for Lincoln's win. Okay, so now we have a quantification, and this allows us to rank causes, to say, okay, this cause is more important than the other one, and to order them by ranking and to reason about most influential one, etc. So it's very useful. Now, the complexity of determining all these problems, right, of deciding decision problems and of actually computing the functions associated with them is quite unpleasant. Right, they're all intractable. So causality is a sigma to complete for singleton causes when a cause is just a single variable, and D to complete in general case where D2 is the class that contains languages that are in the intersection of sigma, of the different class, so of sigma 2 and pi 2, so which is considered to be above, to include both sigma 2 and pi 2. And the responsibility is in the matching functional problem class. So it's functions that are computed with log queries to sigma 2 oracle complete. And this is because we actually, it's not a decision problem, it's a function problem. So yeah, so it's intractable, right? So it's nothing pleasant in these numbers, but it doesn't mean that it's not useful in practice. The reasons why it is actually is useful in practice is because, first of all, there are linear time approximation algorithms, and they are accurate on most problems. Because we know the worst case complexity is usually obtained by using quite contrived problems, or crafted, especially to be difficult. And on most problems, it's not that difficult. So the complexity, actually, I mean, it's doable. And there are linear time approximation algorithms. We usually care only about high-strength causes. So if we limit the responsibility from below, then, for example, only care about causes with responsibility at least third, then it's easy to compute those, polynomial. And finally, so an interesting feature that will allow us to do the things that I'm going to talk about next is that we don't have to know the whole model for the interaction, which is great, right? Which actually what makes it really, feasible. Okay. So now the motivation for applying causal reasoning to modern systems. So modern computerized systems are huge and difficult to understand, and they're becoming more huge and difficult to understand as the time passes. So the code for Apollo in the 1940s, right, to land on the moon for Apollo 11 was about 1962. It was about 40K lines of code, whereas now the code of Facebook is 62 millions of lines of code, and modern cars run hundreds of millions of lines of code, and the code base of Google is, I think, 2 billion lines. So, it means that the systems become bigger and bigger, and the bigger they become, the closer they effectively become to black boxes, right? The closer they are to black boxes. So if you ever heard the discussion about testing and debugging systems, software in Facebook, so they practically always do black box testing because it's just too large to try to figure out what's happening in white box, right? To look inside the code. So they effectively, these large software systems, they black box for all intents and purposes. And not only that, now there are systems that actually by design black box, right, such as deep neural networks, so different types of neural networks that are merged, and they are not even supposed to be understood by people, so they are black boxes by design. Yet, even though we have those systems as black boxes, we still want to be able to answer some very important questions about those systems, such as can we understand and fix errors? Can we explain the system's decisions? Can we trust the system? And is the system fair? And this is part of the question that were named by DARPA as a challenge in explainability of AI systems. And they're also written in the draft of the AI Act, both the UAI Act and the upcoming, right, the UAI Act and upcoming UK AI Act as well. So historically, the first work on applying actual causality and responsibility to systems was in the understanding and fixing errors domain. We explained counterexamples, that was 2009, but I'm not going to talk about it, but just to mention that it was useful. And the discussion about trust is something that is actually requires not only computer scientists, but a collaboration with probably psychologists, sociologists, and ethicists, etc., because trust is something that we cannot measure, quantify accurately. So I'm not going to talk about that either, but I am. So next I'm going to talk about explanations. Can we explain the system's decision? Right? So the system is a black box, but now we're going to use causality to try to explain the system's decision. And there's an example. So I'm taking a neural network that is classifying animals. So it has this image of a red panda, classifies this, and it gives it the label red panda. Okay, so but now we would like to explain its decisions, right? So we would like to say, so it is red panda because, or rather not it is red panda, but this neural network decided that it's red panda because, and what we give here in this work is an explanation. So it is because of this part. So this is a part of the image that is defined as a causal explanation, which is a minimal, sufficient, non-trivial subset of the pixels of the image. So it is sufficient for it to be classified as a panda. So it's like we take and we cover the rest of the image with cardboard, right, with neutral color. We're leaving only this part, and it's still sufficient for it to be a panda. It is minimal such subset. So if we cover a little bit more of that, it will no longer be a panda. And non-trivial because obviously if it's the whole image, then it's not a good explanation, right? So if we cannot cover anything, then I mean, giving whole image as an explanation is not very useful. And this roughly follows the approach of Halpern and Pearl to definition of explanations in causal models. The neural network here is a black box completely intentionally because we're not looking inside the black box at all, right? We're not looking inside the neural network. So how do we compute that? Right, it's a black box causal model. It is, we do consider it being causal models, but more causal model, but we don't look inside. Now, before we discuss how we do that, I would like to note that it's actually very useful also for detecting misclassifications. So we have, there was a paper a while ago, right, that raised the question of misclassifications of wolves and huskies, pictures of wolves and huskies that were given to neural network, and it supposedly it was trained. And then in the classification phase, it said that the picture of a husky is actually a wolf. That was the paper of Why Should I Trust You? That was cited many times since then. And then they looked at the training set, trying to figure out why the misclassification happened. And they realized that all the pictures of wolves in the training set were on the snow and all the pictures of huskies were on the grass, and therefore in the actual data set that they fed to the system, when it saw a husky on the snow, then it categorized it as a wolf because it learned to differentiate between snow and grass rather than between different animals. So in this particular case, it is definitely interesting, and it was first work that discussed this problem. But here, a misclassification is clear when you are looking at the image. Our explanation techniques actually allows us to detect subtle misclassifications. And here is a real example. This is an image from ImageNet. We ran it through the neural network for classifying images, a standard neural network, and it said it's a cowboy hat, which actually seems okay because the picture is of a child wearing a cowboy hat. So, I wouldn't object to it, right? This label seems plausible. But then when we asked for an explanation, the explanation was part of the child's face. Now that's clearly not okay, right? It's not a hat because of the face. And so then we looked at the training set and discovered that all images labeled as cowboy hat were actually of people wearing cowboy hats. So instead of recognizing a hat, the network learned to recognize a face. So this misclassification wouldn't have been discovered without an explanation. So how do we compute an explanation, right? Remember, it is intractable, right? It's very complex, and we don't know the model even. So how do we do that? So first of all, we compute an approximation. But as I said, approximations work well on real-life examples that are not too contrived. So this is an explanation. How did we compute it efficiently? So we used ranking, and ranking was used on responsibility. So we actually computed a ranked list based on the approximate responsibility of elements in this image. And when I say elements, you can go as low as pixels, or you can stop before and have some subsets of the image, like some small areas of the image. And then we greedily started adding them to the explanation from the top of the ranked list, assuming that, of course, the higher the responsibility is, the more chances are that this element will appear in the explanation, until we got the same classification as the original image. And let me just briefly show to you how this approximate ranking works. This one. So the ranking procedure. So first we take the image, we partition it, an image, we partition it into regions. Now we compute responsibility, which is a rank, right, approximate of each region. So now we say so each one is an element. So we check, okay, so let's look at this region. Now this region by itself, so based on the definition of responsibility, now that this is my contingency that I introduced, by covering the rest of the image. And now this is still a panda, but now if I remove this one, the remaining part is no longer going to be a panda, right? So this one is, of course, has high responsibility. And then we order according to the responsibility and throw away relevant regions. So here in this case, we would have this is panda and this is not panda, right? So those, the rest of the regions, let's assume that this is not panda. Definitely, it can be a bear, right, or something else. So those regions are thrown away. And then we continue partitioning only the regions that are left in the ranking, starting with the highest ranked region. So now we continue, we partition this one, we cover, we say, okay, this has responsibility half, and this one has responsibility 0, this part corner, and the bottom corner also has responsibility 0, for example. So we continue with high ranked regions. When do we stop? When we reached a small atomic element. It can be 1 pixel, or it can be a small set of pixels that we define as our stopping condition. So the lower we go, the more fine-grained the explanation is going to be. But if we stop in the middle, it will be just kind of blocky, right? Pixelated, like when you watch a movie and the bandwidth is not enough, so every figures appear like a set of blocks. So this is how it's going to look like a little bit, but it will still be an explanation. And note that this reasoning dependent very, very heavily on the actual partition. So we repeat it many times with different partitions and then take the average. So that's, I think we repeated it 100 times in the experiments and then took the average. So this is how it worked. Now, once they are ranked, the pixels are ranked, the ranking itself is also useful. So it's not, we don't actually have to limit ourselves to an explanation. We can also use the ranking for example, to construct a heat map, which is what I'm going to show in the next slide. So by the way, so this approach, causal approach, because it doesn't assume anything about the structure of explanation, any type of, in particular, it doesn't assume any type of continuity. So it works for non-contiguous explanations as well. And here we have a benchmark set of images with partial occlusion. So this one is a bus. And an explanation actually consists of 2 parts of the bus, right? One from the front and one from the back. So here our tool works much better than others. It assumes some continuity in explanation. And as I said, we can also use the ranking to construct a heat map, right? So here we have a dog partially obscured by the toilet paper. Yeah, in terms of the pandemic, beginning of the pandemic, it was a very sensitive topic of toilet paper, but now we can mention the dog wasting toilet paper. And the ranking shown as a heat map here shows that actually explanation probably resides somewhere around the dog. It's important to note that the toilet paper is not going to be part of an explanation as it shouldn't, right? I mean, it works as expected. So those are explanations. And just so while you are looking at this rapidly moving slide, just a side note, we also have work that shows that this approach of explanations also works to explain and to causally simplify reinforcement learning policies. So we've done it not only with mini-grid examples, but also with Atari games. And indeed, we were able to show that actually very few decisions of deep reinforcement policy are needed in order to obtain the reward, and these decisions can be ranked as well. And then, so on the left, you have the original reinforcement learning policy that goes from the top left corner, passes through the gate and reaches the end, the green square. And on the right, you have a simplified reinforcement learning policy that the triangle, the arrow is blue in those places where it just includes the default, which is a random step or following the previous step, which has nothing to do with the actual learn policy. So you can see that, first of all, it also successfully reaches the end, but also it takes much fewer steps. It's much simpler. And if we want now to explain it, we can only highlight the red areas, the red triangles, and those are much fewer than on the left. Okay, so now we're done with explanations. Again, so you note that we didn't look inside the neural network at all. And now let's talk about fairness, which chronologically is the most recent work out of those that I described. So the motivation for fairness, I think, so it's kind of something that is very easy to sell, right? It's that AI black box systems are widely used everywhere, and their decisions affect people. So, for example, banks, are known to use black box software, proprietary AI, to decide to very important questions about their customers, such as giving them a loan, credit card limit, etc. So it's a very important question to ask whether the system is fair. So here are some examples, right? So this is on the left is a tweet from Steve Wozniak, one of the founders of Apple, who says who supports a previous poster. It's from November 2019, so quite recent, of Apple Card, where an Apple Card decides on a credit limit using an algorithm, and Steve Wozniak says that he and his wife have been married a long time. They have no separate bank or credit cards account, no separate assets at all, and yet he has 10 times the credit limit on his credit card than his wife. It says it's big tech in 2019. And another example is, so those are the headlines of newspapers from 2015. They say that Google's algorithm advertised higher paying job to more men than women. Yes, so two women are less likely to be shown ads for high paid jobs on Google. That was the work of Anupam Datta in 2015. And actually he showed that you can define your preferences for ads and ad settings, but there is some wiggle room still, and they use it to decide to make their own decisions about which ads are going to be shown. And this the result is that women don't see as many ads for high-paying jobs as men. So other decisions based on sensitive attributes, such as race, gender, religion, etc. So sensitive attributes are something that is defined, or protected attributes, something that's defined in law, and it's forbidden to discriminate against based on these attributes. So it's a very important thing to figure out. So we proposed a framework in which, so let's use a running example of mortgage approval. We have a bank with this black box AI system And we have a regulator that is, would like to see whether they can certify the bank's system for fairness, right, and lack of discrimination. So the procedures that we propose, so first of all, it starts with sensitive variables that the regulator has. It's not actually up to discussion or any type of negotiation, because this is defined by law. So gender, ethnicity, age, religion, etc. Right? There are some disability. It is part of the Equal Opportunity Act in the US, and there is an equivalent legislation in the UK. Now, the bank comes with the proposed allowed variables. The allowed variables are those that correlate with sensitive ones, but the bank is justifying them by using business necessity. So the first step is approval of the set of allowed variables. And of course, the disparate impact is different impact of the decision depending on the protected attributes or sensitive variables versus business necessity. So for example, as we know, salary highly correlates with gender because I think women earn about 20% less than men, or even more significant on average. Yet bank may very well claim that they need to know the applicant's salary because it is one of the important characteristics indicating when the person will be able to repay the loan, to repay the mortgage. So this is the type of discussion that is going to take place. So first, we have approval of the allowed variables. This is the first step. Right, so not obvious because salary, for example, correlates with gender, and there are many such discussions in philosophical literature as well. So whether we can take some variables as allowed or not, or whether it will have negative impact on society, which is not justified by business necessity. Now, the next step would be is what the regulator needs to know what data is collected and how the inputs are computed. So when we inputs, we're talking about the inputs to the black box AI system. So we're not looking inside the black box AI, but we need to know what data is collected by the bank and how these inputs are transformed or translated or unified and fed into the system. And why is that? We will see in a second. And so no need to know the whole model or algorithm, which makes it doable and implementable because obviously bank would not like to expose its proprietary IP. Okay. Then being able to compute the output for any setting of input. So basically, regulators should have an access to the system in this it being black box. So to use it, right? So the regulator should be able to see the output of the system on every combination of input. To experiment with it, basically. Okay, then it will say that the system is fair if the following criteria hold. So first of all, so the inputs are obtained as the bank said, and it's acceptable, right? That they are obtained in an acceptable way, and they are reasonable. The system has no disallowed proxy variables. We'll talk about it in a second. No other inputs are used. So we looked at the inputs, they are white box, and we didn't see anything else. And changing the values of sensitive variables while keeping everything else fixed does not change the outcome, which is the system fair? So for the we're going to talk about 2 and 4 in a little bit more detail. But the first one, just briefly, for acceptability, for example, it's not obvious because one of the questions that currently the legal system has in mind is whether the bank has a right to look at the publicly available information on the web, such as, for example, the social network activity of each person. So is it acceptable? So it might not be acceptable if, for example, they learn some protected characteristics from it, such as the religious affiliation. So it might be that the input to the system is not the religious affiliation itself, but it is rather which religious holidays does the person celebrate. But of course, it is not acceptable because it's highly correlated with the religious affiliation, which is a protected attribute. Now let's talk about the proxy variables. So proxy variables is getting information about sensitive variables from disallowed ones. So the ones that actually are not allowed to correlate with sensitive because of business necessity. So there's no business necessity, that allows the bank to use them. So it's not always clear whether variable is a proxy. So here's the example of the social network that I mentioned. It's public information. So you're taking religious holidays from scraping the internet and getting information from the social networks. But it is a proxy for religion and or for ethnicity for some religions. So, so this proxy probably should not be allowed. So we have to look out for it. Even though in the system it is not inherited, right? It is not a descendant of any sensitive variable. It's just a direct input because it was taken from social networks. Another example is that bank can be malicious and hide the proxy in allowed variable. So here is, for example, if we have gender and salary. So salary is an allowed variable and it was given on the forms, but actually when the bank prepares the input for the system, it somehow hides the gender in the salary. For example, by rounding salary of men to the nearest whole pound and adding 50p to a salary of women. Right? And then after that, the decisions are made based on whether the salary has 0.5 at the end or 0.0. So this again can be found. This can be found by looking at the input preparation part, which is a white box. And the unintentional proxies, of course, can be found by looking at the probability distribution and seeing whether there is a significant change in the distribution given this variable. Basically, whether there is a strong correlation. Okay, and now number 4, which is just lucky because I'm almost out of time, as I was told. So changing the value of a sensitive variable while keeping everything else fixed does not change the outcome, which is, is a system fair. So here is the fairness of a system for certification. So a model M system is fair with respect to the set OX sensitive variable and set Y of allowed variables. If for any system, for any setting, for any values of other variables, changing the values of sensitive variables has no effect on the outcome if the allowed variables are fixed. So in other words, if we have Jane, who is a woman applying for a mortgage, and she has, this is her salary, education, current house price, etc., and salary is an allowed variable. So keeping salary fixed and changing Jane to John, the male, will not change the outcome of the mortgage application, whether it's going to be given or not. Now, how can we check this? So the certification process is, of course, the regulator will have to perform some interventions to tweak the data, to change the values of sensitive variables and to feed them in the system while keeping the allowed variables fixed. And it is going to be complete, as I guess you could guess, right? It's there is no other setting that results in different outcomes. So this has an NP-complete flavor. Yes, so NP-complete, great, not wonderful, probably not something that we can do in practice on big systems. But then for a single applicant, which is like verifying a lawsuit, so for a given applicant, Alice, right? So a model system would be fair with respect to the same set X of sensitive variables and the set Y of allowed variables. If for the values describing Alice, changing the values of sensitive variables has no effect for Alice if the allowed variables are fixed. So if we take the values for Alice and we only change sensitive variables for her, then the outcome is going to be the same if everything else is fixed. So it is still going to be complete, but it's polynomial in the number of settings of sensitive variables. So it's exponential in the number of sensitive variables, so polynomial in the number of settings, number of values. But if we have very few sensitive variables, and 3, 4, then it's not that bad, because then we have 2 in the power of 3 or 2 in the power of 4. We have maybe 8, 16 settings to check. It's not that horrible. So for deciding whether Alice has grounds for a lawsuit or not, it should be much more feasible. Right, so the proposed regulation, in summary, will have, so fairness, which we have precise algorithm which is going to complete, or approximation, and statistical independence for proxy variables. And this together should be sufficient for certification of system as fair and non-discriminatory. This is the bibliography. Since it's recorded, you'll be able to look at it. There's also one workshop paper that I forgot to put here, but never mind. Yeah, I think so. That's it. Any questions?
Good. Yeah, thanks for the nice talk. We have some time for questions. I think people can write questions in the chat if they have any.
Yeah.
I can start with some questions that I have myself. The first one is about this procedure that you described for interpretability, where you showed this example of the red panda, and you can partition the image and see how will this kind of the sensitivity to the different regions.
Yep.
My question is, obviously this works for this type of image data, but there are many other prediction settings where you may have tabular data.
Right.
And then my question is regarding, well, how do you deal with
how do we do tabular data, right?
Yeah.
How will we do tabular data? How will we partition? Yeah, we will need another approximation algorithm, right? So the definition that I mentioned here, the formal definition is, minimal sufficient subset is the same, but we will need another algorithm.
I mean, I guess it's just a matter of how you, I can understand this as a type of search for some region.
No, it's not a search, right? Because we're not, in search is something where you're not guaranteed to cover everything, and we do cover everything. So it's not a search. We partition. So the imprecision here stems from the partition into region, which is random, right? So we randomly decide where the lines go. And this we're trying to address by checking many different partitions and then taking the average. Another imprecision comes from the fact that we compute responsibility like on the higher grade, of the big chunks region, then go down. So I can imagine, again, an image hypothetically in which there is one pixel that has a very high responsibility, but around it, there's very low responsibility, right? And it's not, the whole region is not ranked high enough. But this is a very contrived image.
Yeah. Yeah. I mean, I don't know if you could do like some form of partitioning of your features, maybe with some hierarchy. And then
but then we are getting inside the network, right? Or we require more information. This method doesn't require any additional information at all, and it doesn't look inside the network.
Good.
We have a question. Have a raised hand.
Yes. Yes. Meghal, do you want to ask your question?
To understand how this. Am I audible?
Yeah.
Oh, so my question was regarding this same procedure, the ranking procedure, and I wanted to understand how the ranking is done.
How, sorry?
How is the ranking done?
Okay, so we'll start with, I'm on the right slide for that. So we take the image for ranking, right? We're talking about for images. Where we partition into regions. Now for each region, so for example, for this one, do you see my cursor? I don't know if you can see my cursor. For the top right corner, right? So the question would be, if I remove it, will it still be a panda? Right, if I cover it.
But is it sort of like you're training a network to classify whether or you've already trained one, and then
I have a trained network. I'm not retraining it, not retraining it at all. I'm querying it, right? So I should be able to query the system. Sorry?
Okay.
Okay.
Yeah, I get it.
So this is how it's done, and based on the definition of responsibility. Okay, so now we have a question in the chat. What about a fake image with two heads, a two-headed fox, right? The fox from Chernobyl. That should be identified as not a fox, but you can still, yes. But so the assumption is that the image is a fox or a panda, right? We want to explain why it's a panda. We don't want to find an explanation of a panda to something that's not a panda, right? So the setting is different. Okay. So as I said, so what would you like to explain? Why is it not a fox? I didn't note that I didn't talk about explanations of not something. It's highly non-trivial, right? How we define that something is not. Correct? Like for example, here, if you ask me how do you explain why it's not an elephant? So how would you explain it? It's not an elephant. Maybe by saying it's a panda, right? Maybe it's sufficient, but it might be not an animal at all, right? So it's not the framework doesn't translate naturally to negative labels.
Good. I have one question about the example with the policy in the reinforcement learning setting.
Yeah.
The way I understand is that you are able to simplify the policy to obtain one that achieves the same goal.
Exactly, or roughly the same goal, right?
Yeah. Could you explain a bit more how this is done? I think I didn't get it from.
Yeah, sure. It was like, let me see whether I can pause those. Oh, no, I cannot pause those. Sorry, you'll have to suffer through things moving on the screen. Yes, so what we do is we, the elements of that we're trying to modify, the input is similarly to how we covered the panda parts, are pairs state action. So if I'm getting to the state, I'm going to turn left, right? I'm going to turn right. And then we can mutate those and see the effect on the reward. So we can mutate subset very similarly to what we've done with the panda and see whether the reward is still achieved. Or, it depends. If you can say, I'm happy with 80% of the reward, this is my threshold, that's also fine. And this provides us with approximate responsibility. And then we rank these pairs of state action according to their responsibility in achieving the reward. And then we're saying, okay, so how many of those do we need? Again, greedily constructing from the top. And we add them to the policy from the top until we reach this reward, and then we stop. So usually it would be, I think the result was about 20% of the decisions were sufficient to achieve the same reward.
So yeah, the idea is to get rid of these pairs of state and actions that don't really lead to
yes, exactly.
reward.
So if you look at the image on the right, indeed everything that is blue, those are state actions that were removed.
Okay.
Right. So only the red one. So you can see it. So red is to start going down, right, and then to turn, and then it's all blue. Right. You can see, and then it's red to go down again. That's it, right? And that's everything in the middle is blue. And you can plug any random or default policy in between where you removed the active policy decisions. It works similarly.
Good.
I have questions here. Could you elaborate? So I think this was, so Shirley, did I answer your questions? Because this was also Miguel's question. Yes, okay, good. So then we have a question from Daniel. How do you would use such a partition algorithm to identify features that define a group? Yeah, so it's an interesting question, right? Because then we're trying to explain a group of images. Sorry, I'm going to switch to non-moving slide. We're going to identify a group of images and not just one classification. So it is, we definitely have it as a future work, right? We don't know it yet. We are thinking, or, we're conjecturing that is something like a Boolean formula of parts of images, right? It will be like, it has either, I don't know, 4 or tail or 4 legs, right? Where 4 is something that you can detect and 4 legs is a part of the image. So it should be basically similar to the zoological classification. But this is definitely, I mean, it will require more effort.
Good. So I think we are out of time. Thanks a lot, Hana. It's been great.
It was a pleasure
to have you here, and yeah, thanks a lot for your insights on your work. Thanks everyone for joining, and see you at the next seminar. Bye. Bye.
I can send the slides. So there's a question about the slides. I'm happy to send the slides as well. So the recording is going to be available, and I'm happy to send the slides.
Good. Thanks.
Thank you.
Bye.
Thanks.
Bye.
Bye.